Hi, my name is Naoya Takashi. In this work, we present a novel neural network architecture that achieves state-of-the-art results in dense prediction tasks, including semantic segmentation. This work was presented at CVPR 2021. The code and pre-trained model are available in the link on the screen. Dense prediction tasks such as semantic segmentation and audio source separation involve high-resolution inputs and predictions. For this, a model requires to model both local and global structure of data in large input field to produce fine-grained predictions. The local and global patterns in data can depend on each other. A local structure can be more accurately estimated by knowing a global structure and vice versa. Therefore, a frequent interchange of multi-resolution information can be beneficial. Many CNN models have been proposed to model high-resolution data. However, they interchange representations in different resolutions only a few times. For example, ResNet is adapted to semantic segmentation by adding a layer that merges intermediate representations in different resolutions at the end of the ResNet. UNet gradually decreases and then again increase the resolution with skip connections from previous blocks in the same resolution. HRNet is composed of several stages. In each stage, feature maps in different resolutions are first processed by CNNs individually and then aggregated by matching the resolution with other resolutions with up or down sampling at the end of each stage. In these approaches, the multi-resolution fusion are done only a few layers as shown in the green box in the figure. There are several works that fuse multi-resolution information by using dilated conversion with different dilation factors in parallel. Dilated conversion can cause aliasing problem. That is, signal over the next frequency become indistinguishable with lower frequency after subsampling. Therefore, most CNN models first involve standard convolutions that allow to learn an appropriate anti-aliasing filter. However, this prevents to fuse local information in the early layers, and multi-resolution modeling can be performed only on the feature maps in which high-frequency components may be removed. We claimed the importance of a dense simultaneous modeling of multi-resolution representations and proposed a novel CNN architecture called D3Net. The D3Net combines a dense skip connection topology in DenseNet and a novel multi-dilated conversion that allows multi-resolution modeling in almost all layers. In multi-dilated conversion, dilation factors depend on which skip connection the input feature maps come from. The right figure illustrates the third layer of dilated dense block. The dilation factor for feature maps from the initial input is set to 1, and for feature maps from the later layers, dilation factor are increased by factor of 2 as the layer goes deeper. This design of multi-dilated conversion can prevent the aliasing problem that exists in a naive combination of the dense skip connection and dilated convolution, where the dilation factor depends on the depth of the layer, as shown in the left figure. If we look at the convolution in the third layer, which dilation factor is 4, only the feature maps from the second layer, which illustrated in orange, can seamlessly cover entire input field. Applying dilated conversion to the feature maps from the input and the first layer that are illustrated in red and green has blind spot in its receptive field. This can cause the aliasing problem. In contrast, the proposed multidilated conversion has different dilation factor depending on the skip connection so as not to have the blind spot in any feature map. We further nest the dilated dense block or DIT block to provide a flexible modeling capability at each resolution. We also introduce channel reduction mechanism at the beginning and the end of each TD block to mitigate the excessive increase in the number of channels. We called the resulting architecture as D3net. We evaluate D3net in semantic segmentation task on cityscapes. D3net outperforms state-of-the-art backbone network architectures. We also conducted ablation study. When we replace the proposed multidilated convolutions to standard convolutions, the performance drops significantly, probably because the receptive field becomes much smaller without dilation. When we replace the multidilated convolution to a standard dilated convolution, the result becomes even worse, probably due to the aliasing problem. We also evaluate standard dense nets that has similar number of parameters as D3net. Dense nets are significantly outperformed by the D3net even without the multidilated convolution. This validates the effectiveness of the nested architecture in D3net. Finally, we also combined D3net with OCRnet method and obtained state-of-the-art result. To demonstrate the generality of the proposed architecture, we tested D3net on other tasks in audio domain. Music source separation aims at separating music to individual instrumental tracks. As the source separation is often performed in frequency domain, the problem is somewhat similar to an image segmentation problem because a model accepts two-dimensional spectrogram and predicts the magnitude of each source at each frequency beams instead of class labels. In our experiment on MUSDV, where the goal is to separate music to vocal, drums, bass, and other, we again obtained state-of-the-art results. We also applied D3net to the task for simultaneously identifying the type of sound and the direction of arrival from multi-channel recordings. We participated in DK's challenge, which is the biggest challenge for the same task, and our system that uses D3net won the first place. From this result, we observe generality of D3net in the variety of tasks. Conclusion: we propose D3net that combines a dense skip connection and dilated conversion to perform multi-resolution modeling in almost all layers while preventing the aliasing problem by introducing multi-dilated convolution. D3net achieves state-of-the-art results on semantic segmentation task and music source separation task. The code is available online, so please check it out. Thanks for watching.
Hi, this is Tokuhiro Nishikawa from Sony. I'd like to talk about dual normalization multitasking for audio-visual sounding object localization. This video is based on this paper, so please check out the paper for further details. The problem of audio-visual sounding object localization is given a short video clip with audio as input and visually visually locating a sound source in the video. The mainstream of audiovisual sounding object localization is based on self-supervised or weakly supervised learning, which achieves localization without any supervisory data indicating the location of sound. One of the challenges is ambiguity of the visual location of sound. Music instruments are designed to produce sound, so there is little ambiguity of the location of sound source. However, for example, in this scene with chainsaw is used to cut logs, the sound of the engine and the blade rotating and the vibration of the wood are all mixed, and making it difficult to determine the actual physical source of the sound. Because of this difficulty, no datasets and metrics have been proposed in the literature to quantitatively evaluate localization performance in unconstrained videos. So we need criteria to annotate the location of the sound source. Here we propose to annotate the object, which is the original cause of the sound. For example, in the chainsaw scene, we annotate the region of chainsaw and ignored the other factors. And we created annotations for the videos in the test set of unconstrained AVE dataset. And for each 10 seconds video in the test set of AVE dataset, we created bounding box annotations manually for sounding objects at 10 FPS. So there are two common training tasks. The one is audiovisual correspondence task, or the ABC task. The model should run to determine whether the pair of video frames and audio clips correspond to each other or not. Positive pairs are extracted from the same time of one video, while negatives are from different videos. The advantage of ABC task is it is completely self-supervised, but the disadvantage is that the audio is often mixed with out-of-view sounds or ambient sounds that is not directly related to the visible events. Another task is audiovisual event classification task, where the model should predict the class of the audiovisual event. The advantage is that it is guaranteed that the audio contains a sound from the target object always, because annotations are made by humans. And in both tasks, the localization is done by some kind of attention mechanism in audiovisual fusion layers, and we don't yet have a known strategy on how to utilize these two tasks together to improve localization performance. In preliminary experiments, we found that ABC is good at locating wide region of the sounding object, but sometimes it locates areas around them. On the other hand, AVEC is good at finding globally important points to classify the category of sounding object. From these findings, we propose dual normalization tasking. Given a pair of video and audio, the model first extracts the visual and audio features, and the extracted features are fused to create pixel-wise audiovisual similarity map. And then we normalize the map in two ways, locally and globally. In local normalization, each pixel of the similarity map is processed independently, and each normalized value is used as an instance for multiple instance learning to estimate audiovisual correspondence. And globally normalization pixels is to select the most discriminative pixels by considering their relations to the entire audiovisual similarity map, and it serves as the attention to the visual features to solve AVEC. And about the audio-visual fusion, in addition to normal static fusions, we proposed a new fusion method that is called combined dynamic fusion, and it extracts the dynamic correlation between audio and video by using recurrent neural networks. Here is experimental setups. We used two visual backbones for comparison. One is VGZ19 pre-trained with ImageNet, and another one is i3D's RGB stream pre-trained with Kinetics dataset. And we used two evaluation metrics. Heatmap box AUC is the area under the curve of heatmap output, and the bounding box ground truth. It is better if the heatmap is spread out in the target bounding box. And PIBR, or peak in box ratio, is better if the location of the heatmap peak is correctly in the ground truth bounding box. And this is the result. We set two baselines for model comparison. And in addition to the two baselines, to validate the effectiveness of DNM, we compared models trained on a single task, either AVC or AVEC. The two DNM models with both backbones showed a significant improvement in AUC from the single task conditions. The qualitative results showed that the models with DNM did not show the problems which occurred in the single task conditions, such as pinpoint localization or edge localization. And when CDF is used for audio-visual fusion, the performance is even better compared to their static fusion counterparts. And let's see some videos.
Começa já na segunda oitava, no dó da segunda oitava.
So for the first time in this field, we created a dataset and evaluation metrics for the quantitative comparisons of audio-visual sounding object localizations in unconstrained videos. And we proposed DNM, which effectively connects AVC and AVEC task, and it outperformed the baselines in all metrics. Please check our paper for details and datasets. Thank you very much for listening.
Hi, this is Andrew Shin from Sony, and I'd like to talk about transformer architecture for cross-modal tasks with vision and language. This video is based on two of our papers on the topic, so please check out the papers for further details. So cross-modal tasks with vision and language have conventionally been dominated by CNN and LSTM approach, where CNN is used for vision representation and LSTM is used for language representation. And there were other variations, such as how they combine each representation into common embedding space, but the fundamental backbone has almost invariably been restricted to CNN and LSTM approach. Then the transformer came out, and many other variations, including BERT and GPT-3 followed, and demonstrated state-of-the-art performances in natural language processing and speech recognition tasks, rapidly replacing LSTM. And transformer has also been employed for models dealing with vision and language, and many variations have been proposed, including VLBERT, LXMERT, VLBERT, and many more. So all these models have the following in common. They embed the language with BERT, and for the image part, they tokenize the image with region detection models, such as FastRCNN or FasterRCNN. So the question is, what are their differences and what contributes to the model's performance? Well, some of the major factors include pre-training objectives, pre-training dataset size and model size, and network architecture. So let's go back to BERT for a moment. BERT actually proposed two unique pre-training objectives, one of which is masked language modeling, where the language model is trained while learning to recover the masked tokens. And the other one is next sentence prediction, where the model learns to classify whether two sentences are supposed to be adjacent or not. So how do we extend this task to cross-modal setting? Well, it turns out that masked language modeling can be used as is, since cross-modal setting also involves language part. And some of the models employ visual clue to aid this process. And the next sentence prediction is mostly imitated as image sentence matching rather than two sentences, with the sequence of regions rather than word tokens being the input for the other modality. Many models also proposed masked visual modeling, which is kind of the porting of the masked language modeling to the image domain, where they mask some of the regions and try to classify the content of the region or regress the feature of the region. And in this case, they mostly use fast RCNN prediction as the ground truth, and some models also attempt to leverage linguistic clues. Other pre-training objectives include image QA or captioning, etc. So combining these categories with variations, we can make lots of different combinations of pre-training objectives as shown in this table. Another factor is the size of the dataset used for pre-training. Most of them are pre-trained with image and caption pairs. And the number of pairs ranges from 500,000 to more than 10 millions, with large dataset size usually leading to better performance. And the model size also turns out to be a critical factor, and with everything else being equal, larger models almost always perform better. And the network architecture can be roughly divided into two categories. One is single stream, which is a straightforward extension of transformer to account for the region tokens as well. And the other one is two stream, where they explicitly intermingle two modalities at each transformer block. So these multiple factors contribute to the model's performance, but please check out our paper for further details on each factor's more specific contribution. And one thing I'd like to point out is that although these models used transformer encoder for the image representation, they still relied on the CNN for the image features itself. So is it possible to represent the images with transformer without reliance on CNN? Well, Vision Transformer has recently been introduced. It's a transformer exclusive model for vision representation and demonstrated comparable performance to CNN for image classification tasks. It also implies that reliance on CNN can be completely eliminated for cross-model setting, and some of the recent papers indeed proposed the models that are entirely based on transformer and not relying on CNN. We also examined the transformer exclusive model in one of our recent papers and demonstrated that a very simple combination of Vision Transformer and BERT can accomplish comparable performance to CNN-based models. So in conclusion, conventional CNN LSTM-based approach for vision and language tasks have been replaced by transformer-based models, and multiple aspects contribute to their performance, especially the unique combination of pre-training objectives. And with the advent of Vision Transformer, transformer exclusive models have started to appear. And please check out our papers for more details. And thank you very much for listening.